Every day, millions of people use public transport to get from point A to point B. But have you ever wondered how transit agencies predict where everyone wants to go? Today we're diving into the world of short-term origin-destination demand prediction. It's like a weather forecast, but for people's travel plans. Current modeling approaches that predict movement from an origin to a destination mostly consider long-term patterns on a monthly, yearly, or even decadal horizon. This long-term understanding allows us to appropriately schedule our services, deploy staff, and plan for future service network extensions or alterations. However, let us consider a subway station in the heart of a busy city. During normal operations, people come to the platform often having passed a fare gate or a ticket check, board their train, and alight somewhere downstream to the station. Trains come and go, and platforms fill up quickly, especially during the morning when everyone is heading to work, and then again in the evening when they are heading home. This pattern results in two peaks of passenger counts throughout the day. During these very busy periods, the platform can be at capacity, or, even worse, crowded. These situations can threaten operational efficiency and customer experience, as trains will need to operate slower and the whole journey will become a squeeze. Without high-resolution short-term predictions of where people will start and end their journey, transit agencies are in the dark as to when and how to deploy mitigation measures such as increases in security personnel, slowing down the fare gates, or even closing certain stations of the network close to event venues such as stadiums and concert halls. Therefore, Tinos and I asked ourselves, how can we accurately predict short-term origin-destination demand? Knowing when and where people wanted to go would give transit agencies a good proxy to understand how crowded a platform would eventually become. Obviously, this is not simple and straightforward, as not only do our predictions matter, but also the uncertainty we have in them. Therefore, we set out on a quest.
We first examined data from the Washington, D.C. WMATA and found that we could extract origin-destination matrices binned into 15-minute cumulative values. To get a sense of the data, we first looked at monthly origin-destination matrices and found that they were sparse and consistent from one month to the next. Looking at the flow between the two station pairs, we see that the value histogram is highly zero-inflated and bimodal, which means that we have the biggest peak at 0 and then another peak at higher values. When we saw these images, one after the other, we thought, what if we take some origin-destination matrices and try to predict the next one? We then realized that this is essentially a video, and the problem is the same as that of next frame prediction in the computer vision domain. So, we replicated from scratch one of the most successful convolutional neural network, residual network, or ResNet for short. We have adapted it to accept any size of input origin-destination matrices and allow for any number of time steps to be considered for the prediction. This way, our approach can be adapted and applied to any network and context. The network outputs two matrices of the same size, so two n by n square matrices, where n is the number of stations. One matrix describes the mean next step predictions for all the origin-destination pairs, while the other describes the variance of each prediction. The exciting thing here is that we can adapt the network output to be any distributional parameter for several different probability distributions, such as Gaussian, as in our example, or exponential, uniform, Cauchy, or log normal, to name a few. As a first step, we needed to validate that our network could learn anything. Therefore, we designed a 10-station toy example, which assumes a constant Gaussian mean and variance over time for each origin-destination flow, training a ResNet with 18 layers, minimizing the negative Gaussian log likelihood loss between the predicted mean and variance, and the ground truth target leads to astonishing results after only a few epochs. Here is an example of one of the generated origin-destination pairs, closely fitting the actual distribution to the data. As we have seen, our data is not Gaussian distributed and static over time. Therefore, for our second experiment, we introduced the time context we have seen previously in the real data, when we looked at the morning and afternoon peaks. We create a second toy dataset that features two peaks representing the morning and afternoon rush hours. We take this as our mean and then sample with some variance along that mean. Similarly to before, The means and the variances change between different origin and destination pairs to make sure we make the dataset realistic enough. After training the network, we found that the predictions and ground truth overlap, showing that our network also performs well in this more real context. These results, we pave the way for more exploration and applying our approach to real data.
This work has shown that we can use concepts from computer vision and apply them to a transportation context. Specifically, we showed that we can use a highly efficient ResNet 18 architecture to capture spatio-temporal relations and predict future origin-destination demand with uncertainty. This way, we hope that transit agencies worldwide will be able to predict platform crowding ahead of time, enabling the implementation of mitigation strategies, allowing everyone to have a safer, more enjoyable, and more efficient ride.